Okay, so in the last class, we talked about solubility and solutions. And then we moved on to Henry's law and Raoult's law. So we stopped somewhere around the beginning of Raoult's law. Today, we'll be continuing the class with Raoult's law. All right, so from the last class, we explained the relationship between an ideal mixture. It's quite distracting. Relationship between an ideal mixture and how it affects the vapor pressure of a solution. So when you make any mixture of liquids, you have to break the existing intermolecular attractions. Remember, we talked about ideal mixture, and we said when you have solutions of almost the same intermolecular force of attraction, you would expect that the tendency of, say, solution A, which is the pure solution, the tendency of forming vapor from solution A with the tendency of forming vapor with of solution B should be the same if they are ideal mixture. So once you have these two solutions in mixture, since their rate of vaporization is almost the same because of the almost equal. I need to mute everyone just a minute. Because of the almost equal forces of attraction. Okay, I think everyone is muted now. All right. Okay, so because of the almost equal force of attraction between them, you expect that the rate at which they both form vapor will be the same. So when you have the molecules, when you have solution A and you have solution B, when you mix solution A and solution B to form an ideal mixture, then the rate of their vaporization is the same. So it doesn't really matter the kind of bond you have between molecules of A, and so you have A. So let's assume, because for every solution, there's some kind of bonding between them. So you have solution AA, solution BB, that's the first one is the pure solution A, and the other one is the pure solution B. When you have them in mixture, the kind of bond you probably have is AB. So we're saying that for an ideal mixture, the AA bond is the same thing as the BB bond and the same thing as the AB bond. Now, when you make any mixture of liquids, you have to break the existing intermolecular attractions, which needs energy, and then remake new ones, which releases energies. If all these attractions are the same, there won't be any heat either evolved or absorbed. That means that an ideal mixture of two liquids will have zero enthalpy change of mixing. If the temperature rises or falls, when you mix the two liquids, then the mixture isn't ideal. Now we are talking about the enthalpy change of mixing. Now, talking about the enthalpy change of mixing, when you have an ideal mixture, an ideal solution, when you have an ideal mixture of solutions, there shouldn't be change in the energy evolved or the energy absorbed by the solution. All right, so there are several ways of stating Raoult's law. Remember that Henry's law. Okay, as a quick reminder, let's have the mathematical expression of the Henry's law in the chat box. Chat. I hope I'm not. Oh, fantastic. Okay, I was wondering if I was muted or not. Okay, so I have Tai. Okay, good. So we have concentration. That's the concentration of the solute is equal to Kp, isn't it? Where K is the Henry's What do I have there? Oh, fine, Tife. Okay, Lawal, thank you. All right. So today, Raoult's law, for you to really define Raoult's law, you need two situations. First, you need to define Raoult law as applied to non-volatile solutes, and then Raoult law as applied to two volatile liquids. So in a solution, you can have a volatile solute being dissolved in another volatile solvent. The Raoult law is a bit different from when you have it as non-volatile solute in a volatile solvent. So Raoult law as applied to two volatile components. When you apply Raoult's law to two volatile components, it states that the partial vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component at that temperature multiplied by its mole fraction in the mixture. The partial vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component at that temperature multiplied by its mole fraction in the mixture. So it means that when you have component A and component B in a mixture, you can determine the partial pressure of each of these components in the mixture. So you know that when you mix two solvents, or when you have a solution, so you have two components in a solution, for instance, the vapor pressure of each of those components will definitely change. It's either it becomes lower or becomes higher. So in equation form, for a mixture of liquids A and B, you have PA, which is the partial pressure of component A in the mixture, is equal to XA times P naught A. XA is the mole fraction of A in the mixture, and P naught A is the vapor pressure of A, of the pure component A. That is when it's not in the solution, it's not in the mixture with another liquid. The same thing with the partial pressure of B. You can also calculate the partial pressure of B to be equal to the mole ratio of B multiplied by the vapor pressure of the pure B, okay, this P and B, of the pure B liquid. So in this equation, PA and PB are the partial vapor pressures of the components A and B. The total vapor pressure of the mixture, remember that this initial is the partial pressure. Both of them are going to exert pressure in the solution. Okay, when you have a pure solution, when you have a pure liquid that is volatile, you expect that at a particular temperature, the the molecules in that solvent can gain some energy to change to vapor. And this vapor is now going to interact with the molecule on the surface of what you have in your solvent. So there's going to be some particles on the surface of the liquid that has not gained enough momentum, that has not gained enough energy. This is going to be in some kind of dynamic equilibrium with the vapor that you already have in the closed system. Now it's going to get to some kind of equilibrium, and then that's going to determine the pressure of that particular liquid. So when you have a mixture come into it, what you now have is not just the pure component of A, but now you have some particles or some molecules of B interacting at that level, and then the vapor pressure would also change until it attains a dynamic equilibrium. So the partial pressure A and the partial pressure B, the summation of these two partial pressure will give you the new vapor pressure of the mixture. So the vapor pressure of the mixture is definitely going to be different from the vapor pressure of the pure components that you have. And for you to get the total vapor pressure of this new mixture that we just made, we need to sum up the partial pressure of A in that mixture and the partial pressure of B in the mixture. The P naught values are the vapor pressures of A and B if they were on their own as pure liquids. Now, XA and XB, like I earlier said, are the mole fractions of A and B. And that is exactly what it says. It is the fraction of the total number of moles present, which is A or B. So when you have a mixture, for example, you can easily calculate the number of moles of each of these components. Now, for solution A, you have a certain number of moles of the A molecules that is there. For solution B, you have a certain amount of the number of moles. Now, when you mix these two together, their partial pressure is going to be, for instance, for liquid A, the mole fraction of liquid A now become the number of moles of A divided by the total number of moles. Remember your ratio in, I think, primary school, right? So you have your mole fraction of XA to be mole of A and then total number moles of the solution. Now I have an example on this slide. Suppose you had a mixture of 2 moles of methanol and 1 mole of ethanol at a particular temperature. The vapor pressure of pure methanol at this temperature is 81 kilopascal, and the vapor pressure of pure ethanol is 45 kilopascal. How do we find the total vapor pressure of this mixture? So in this mixture, when you mix A and B, you have a total of 3 moles in the mixture. So it means that for methanol, which is 2 moles, the mole fraction of methanol now becomes 2 divided by 2 plus 1, which is 2 over 3. And then the mole fraction of ethanol, because from the question we have 1 mole of ethanol. The mole fraction of ethanol is now 1 divided by 3. Now you can easily find the partial pressures using Raoult's law, assuming that a mixture of methanol and ethanol is ideal. Remember that when we're talking about those mixtures, we're talking about ideal solutions. So we're talking Raoult law, you're talking about ideal solutions. Now for the partial pressure of ethanol, remember the formula, the mole fraction multiplied by the vapor pressure of the pure liquid. And the vapor pressure of ethanol was given to be, the vapor pressure of pure ethanol is 45 kilopascal. That's why this is 1 over 3 multiplied by 45. And what you have is 15 kilopascal. And in the case of methanol, what you have is 2 moles of methanol, 2 divided by 3 times 81. And what you have is 54 kilopascal. Now, total vapor pressure is equal to 54 plus 15, which is 69 kilopascal. Can be seen that for both, there is, okay, let me ask, what did you notice from the final vapor pressure of the mixture? Is it higher or lower? Please, we need to be fast. Is it higher or lower? The final vapor pressure from our calculation, is it higher or lower than when they are in pure solutions? Okay, good. Some say higher, some say lower. Okay. It depends on what you are looking at. Now, the partial pressure, I want you to look at the partial pressure and the pressure of the pure solutions. I'm not talking about the total pressure here. The partial pressure and the vapor pressure of the pure liquid. Is it higher or lower? Because why I'm asking this question is we're going to get to a point where we talk about what is happening here. And some of you might be familiar with what is happening here. So why do you think it's lower? What property? Okay, let me put it that way. What property do we term this as? Where you have the partial pressure of your mixture lower than its pressure, the pressure of the pure liquid. Anyone? I really don't expect you to know it now, except you were very attentive during your FSC 112 class. What property What property of the solution? Impurities. Well, impurities, well, yes. How many of you have heard of colligative property? Colligative property. Okay, yes, just say yes or no. Colligative property. Okay, somebody said hi. Yes, I am. So why didn't you mention colligative property? Evans is okay. We're going to get to colligative property much more later in the course. All right, please, let's move on. Now, Raoult's law as applied to non-volatile solutes. The vapor pressure of a solution of a non-volatile solute is equal to the vapor pressure of the pure solvent at that temperature multiplied by its mole fraction. Now, the major difference, the major difference between the Raoult law as applied to non-volatile solute and Raoult law as applied to volatile mixture is that in the case of the volatile mixture, you are going to consider the mole ratio and the vapor pressure of each component. But in this case, the determining factor is the mole ratio of the solvent and the vapor pressure of the solvent. So in this equation, you have P is equal to the mole ratio of solvent multiplied by the vapor pressure of the pure solvent, where P naught is the vapor pressure of the pure solvent at a particular temperature. Now you can calculate your mole ratio, or if you want to determine the mass or the number of moles of your solvent that is present in the mixture, you can make your X solvent the subject of formula. And once you know your X solvent, you can say the moles of solvent divided by the total number of moles is equal to your mole ratio of the solvent. And then you can determine the moles of the solvent. From here, you can determine the mass of your solvent. We should have an opportunity to solve one or two. Oh, fantastic. So based on the equations that we have given earlier in the slide, let's look at this question. We're going to solve it together. I don't have a slide on it that is solved. So everybody get your pen, get your paper, get your calculator handy, because we are solving this together right here and right now. You're going to get some more questions for you to practice. So you have 80 grams of C12H22O11, your glucose, was dissolved in 100 ml of water. What is the expected vapor pressure of this solution at 25 degrees centigrade? So number one thing I want you to answer quickly in the chat box is, which of these are we looking at? Is it non-volatile solute or volatile solute? So if it's non-volatile, type non-volatile. If it is volatile, type volatile. Quickly, we have just 1 minute to do that. Is it volatile or non-volatile? Non-volatile, fantastic. Thank you, Francis. Thank you, Oluwatife. Okay, a couple of guys have said thank you, thank you, thank you. So everyone, this is non-volatile, and this means we are using one of this. We're using the X naught solvent and the P naught solvent. We are using the X solvent, that's the mole ratio of the solvent, and the P not solvent to calculate this equation here. Because they are because the non-volatile solute, we're using this equation here. So you have your P is equal to X solvent plus P not solvent. And what were we asked to calculate? We're asked to calculate the expected vapor pressure. Your expected vapor pressure, this is what, excuse me, this is what you have been asked to calculate. So you're going to work out your mole ratio, and your P naught has been given. What's your P naught given as? Your P naught is given as 0.0317. Please take note of the decimal point. 0.0317 torr. That's the vapor pressure of the pure solvent. Now, one other thing that may want to confuse you is working out the mole ratio of the solvent. Remember, this is the mass of the solute. If you have got your answer, please type it. Oh, I'm beginning to see some answers. Somebody said 10.84. Is 10.84? Is it 10.84? Are you sure? Are you sure? Victory. Check it again. Okay, so this is the mass. This is the mass of your solute. This is your solute, and this is your solvent. Your water is in volume. So you need the density of water to work out the mass of water. But we know that the density in gram per mil of water is 1 gram per mil. So it doesn't change anything. So your mass of water is 100 gram. For you to determine the number of moles of water is mass divided by molar mass, which is 100 divided by 18. Oluwayemisi, it's amazing where you are receiving your class. Oluwayemisi Adegoke, you don't have to talk. It's amazing how you are receiving your lecture. I can't see you solving anything. Okay, so from here, you can work out your number of moles, the number of moles of water, which will be 100 divided by 18. Victory, I'm waiting for you to confirm this answer. I'm waiting for you to confirm this answer. So you have your water, number of moles is 100 divided by 18. And then you also have to work out the molar mass, or maybe we should take it one after the other. Okay, so everyone, what's the number of moles of water? Number of moles of water, quickly. 5.5 moles. Thank you, Victory. That's fine. 5.5. Okay, good. So we are all on the same page. We are all on the same page. What's the number of moles of glucose? What's the number of moles of sugar? Sugar, we have moved on. We have moved on from water. Sugar now. Number of moles of sugar, 0.0234. Okay, is that 0.02? Yeah, no. Are you sure it's 0.0234? What's the molar mass of the sugar? That's 80 gram, not 8.0. Somebody is saying, okay, somebody is saying, how did we get 5.55, please? Casey, your 5.55 is gotten from the number of moles of water, which is 100 divided by 18. 100 divided by 18, you will get 5.56. Thank you, Victory. The molar mass of the sugar is 342. No, you can't get 4.15 for the sugar. It's not, yes, thank you, Dewale. The number of moles for the sugar is 0.234. So if you don't have 0.234 as your number of moles for sugar, it's wrong. The number of moles for your sugar is 0.234, and the number of moles for water is 13.89. Well done, Juwonlo. Okay, so the next thing we want to do is to now find the mole ratio. So we go, okay, let's just solve it. Your P is equal to X solvent P naught. Your X solvent now is 0.234 over the total. I'm sorry, but how did you get the 8? 18 is the molar mass. Boluwatife, come on. Boluwatife, the 18 is the molar mass of your water. Water is H2O. O is 16, which is oxygen, plus 2 from H. So H2, 2 times 1, plus 16, 18. That's your molar mass. Oh, okay. Okay, fine. You see, not solving this on the slide is very intentional. I'm still getting 0. No, Olajuni, 80, which is the mass of the sugar, divided by 342, which is the molar mass of the sugar. Calculate the molar mass of your sugar. If it's 342, 80 divided by 342 is 0.234. Do that and confirm quickly that you have the correct value. Olajuni, do that and confirm quickly that you have the correct value. Number of moles is mass over molar mass. Oh, okay. I was using 8.0. Okay, it is 80, not 8.0. Oh, fantastic. Oshideko, number of moles is mass over molar mass. Mass over molar mass. Molar mass of sugar, Tolu, you have C12, H22, O11. So C, the atomic mass of carbon is 12. That's 12 times 12. You have to work out the molar mass of the sugar or shideko. You have to work it out. You have to calculate your molar mass. The molecular formula has been given. So you know your carbon is 12, hydrogen is 1, oxygen is 16. So when you go 12 times 12 plus 22 times 1 plus 16 times 11, the total of that will give you 342. And 80 divided by 342 should give you 0.234. Okay, so let's move on. Now, for you to calculate the P, before I go to the final step, does anyone have a value for P now? Do you have, if you have a value for, okay, somebody 0.043, new answer, okay. Okay, new answer 0.043. Is that the correct answer? I don't think so. Victory. You are using the mole ratio of your solvent. Okay, good. Good. So let's do this. You have the mole ratio of your solvent is 5 points. What? Oh, okay. Good. So when somebody says 1, no, that's 5.56 divided by 5.794 times the vapor pressure. That's in pure solution, 0.0317. 0.03. Victory, that's what you have, 0.0304. David, well done. 304, 0.0304. Okay, I think more people are coming up. 0.0304. I hope you calculated it. Can we use molecular formula of a compound to calculate the number of moles of sugar since we don't have the mass? You have the mass of sugar, which is 80 grams. 0. Okay, fantastic. Oh, good. 0.12, no, I don't know where that is coming from, Victory. 0.03, good. So the correct answer is 0.0304 tall. Victory, well done, thank you. Odunte Mowo, thank you. Adebayo, thank you. Okay, so for some of you that still don't get this, I will send the slide of this solution to your group. Okay, don't worry, I'll send this particular slide to your group. Just watch out after the class. All right, so I also have practice questions for you. You are to practice this, and I'm going to ask you for your answer on tomorrow. I think tomorrow is fine. Tomorrow it's perfect. I'm going to ask for the answer in your group tomorrow. So you have your practice questions, and then we need to move quickly. So why does this matter? Why does Raoult's law? Why does it matter? Why? What's the significance? So remember that vapor pressure determines the boiling point of a liquid. If you had solutes, it will change the solvent vapor pressure. Yeah, we can see that from our previous calculations. Therefore, the boiling point also changes. Now, remember that from the previous examples that we have talked about, we saw that there is a lowering of vapor pressure because of the presence of the solute. That's one of the colligative properties. Boiling point elevation is another colligative property. So when you have solute dissolved in a solvent, so you have solute dissolved in a solvent, there is going to be boiling point elevation of the mixture. So you have two liquids, and then you dissolve, or you have a liquid or a solvent, and you dissolve a solute in it. There's definitely going to be boiling point elevation and freezing point depression. Freezing point depression. So the boiling point of this new solution will increase, and the melting point will reduce. So that's the effect of a non-volatile solute on the melting and freezing point of the solution. And that's why it's good for us to have an idea of what Raoult's law is talking about, such that we'll be able to apply it to our working solutions. Okay, I'm not following what you have in the chat. Somebody is saying any formula to find mass of any substance when not given. Oh, okay, who is this person? I think that's Oshideko. Oshideko, you really need to look at that example very well. Adedamola, where's your writing pen? Your pen and your paper, Adedamola. Okay. All right, so okay, so the boiling point diagram. So like I said, liquid with high vapor pressure will have a lower boiling point, and liquid with low vapor pressure will have a higher boiling point. We're going to see a representative of this. So we have the liquid composition, and then we have the vapor composition. So this is the boiling point of the pure one. So when you have your mixture, when you have it in mixture, there's going to be an elevation of the boiling point. Boiling point elevation, quickly, the boiling point elevation is directly proportional to the molality of the solute. The boiling point elevation is directly proportional to the molality of the solute. So what you have is change in temperature, which is your boiling point elevation, and your molar boiling point elevation constant, which is Kpp, multiplied by your molar, that's the your solute, the molality of the solute. Note, molality is different from molarity. So please take notes, molality, and I'm sure you know that by now. So we have a quick example. How many grams? I don't know how we're going to do this in this short time. Anyway, but we'll try. So how many grams, this example quickly, how many grams of ethylene glycol, and you have the molecular formula of your ethylene glycol here, do you have to add to 125 gram of water to increase the boiling point by 1 degree Celsius? I want you to answer this quickly. So you have your boiling point. The formula you're going to use is here. To increase the boiling point by 1 degree Celsius. So your change in T is 1. Your K has been given as 0.5121. So your M, you make M the subject of formula. So quickly, what's your M? What's your M quickly? Difference between molarity and molality. Interesting. I think you should work that out. Idris, molality and molarity. You will see a slight difference on this slide if you're able to grasp it. So you see what molality is, and then you compare it with what you know about molarity. So quickly, what's the molality? What's M? When you substitute 1 for change in temperature and you substitute 0.5121 as K, what is your M? 0.4 is that 0.4? Oh, maybe I think you're probably giving the final answer. Well, okay, fantastic. M is 1.9. Okay, Adeyemi, I see. Mosuro, thank you. That's 1.953. Fantastic. So that's it. That is M. Now, your molality is equal to number of moles of the solute divided by number of moles of the solute divided by the mass of the solvent in kilogram. So you need to work out the mass of the solvent. So I'm waiting for answer. Whew. Molality, which is 1.9. Okay, so someone is sending his answer 243. 243. Okay, is that what you have? So when you substitute 1.953 multiplied by, yes, okay, your molality is 1.953 and the mass of your solvent, let's see, this is your solvent, 125 gram. So divided by 0.125. So your number of moles, your molality is N divided by mass in kilograms. So your number of moles is equal to 1.953 times 0.125. Okay, somebody already gave us the final answer. David said 15.62. Okay, I think what I have here is 15.1. Okay, that's fine. 16. Banjo, I see you. Okay, fine. That's good. Okay, so that's how you calculate your boiling point elevation. That's how you calculate your boiling point. Oh, good. Okay, well done. So let's move on to the next question quickly. Okay, so on this slide, I have the answer on this slide. So I've covered it up with this. So I want you to quickly solve this and give me the final answer. So it says a solution prepared from 1.25 gram of oil of winter grain, that's methyl salicylate, in 99.0 gram of benzene has a boiling point of 80. Oh, Olajuni. Okay, unfortunately, I don't have the slide here. I'm going to send the slide to you. All the examples we treated in class today, I'm going to send the slide to. So watch out for it. Your class rep is going to communicate with you. We'll send it out to you so that you can locate yourself. It's okay. You don't have to put on that sad face, Olajuni. All right, so if you're with us in the class, if you really understand what is going on, I want you to try to solve this example. What's is it, now, Adeyemi, you're saying morality. Is it molality or, so you need to correct it. Is it molarity or molality? So what we have is, what we're talking about today is molality. And I've typed that in the chat box. Okay, so Dewale has sent it in. It says moles of solute divided by mass of solvent. Thank you. So what do we have? What do we have as answer? Okay, M. That's for molality. Oshideko. That's for molality. Moles of solute divided by mass of solvent in kilogram. Molality. In kilogram, please. Mass of solvent in kilogram. I'm not sending it directly to you. Okay. All right, so for this next example, you have a solution prepared from 1.25 gram of oil of wintergreen, a 99.0 gram of benzene, which has a boiling point of 80.316. So this 80.316 is the new boiling point. Is the new boiling point. Determine the molar mass of the compound. Benzene's normal boiling point is 80.10. So when wintergreen was dissolved in benzene, the new boiling point was 80.3. So for you to find, remember the formula is change in T is equal to K times molality. So what you need to work out first is the molality. Now your change in T would be 80.3 minus 80.1. If you did that, the answer should be 0.21. 0.21 is equal to this K, which is 2.53 times the molality. Now, when you make molality the subject of formula, it becomes change in temperature divided by K, which is then, the change in temperature is 0.21. So 0.21 divided by 2.53. So when you have when you have that, your M is equal to 0. Thank you. Are you sure? This 1.452 times 10 raised to power minus. All right, anyway, so what you have now is, the answer is 152 actually, but not kilo. I don't know what you are getting. It's supposed to be 152 gram per mole. So once, yes, okay, Evans. So once you do that, your molality is equal to 0.0. Okay, thank you, David, is 0.083. Now, molality is number of moles of solute divided by mass of solvent in kilogram. So your mass of solvent in kilogram, this is your solvent here, 99. So in kilogram, it becomes 0.099. So your molar mass is equal to mass, your molar mass is equal to number of moles divided by molar mass, which is 0.00, which is 0.083 times 0.099. That becomes your number of moles. So here, your answer is 152. I want to escape this so I can remove what I used in covering it. So what you have is 152 grams per mole. If you didn't get this, then you are wrong. I'll send you the slide for all the examples we talked about in this class today. It was intentional because a lot of you just wait for the solution. You don't try it at all. Molality, when you're looking, your molality is number of moles, so it is mole per kg. Is number of moles divided by, okay, please, Victory, ask your question. Victory, ask your question, please. Oh, would you like to speak? Let me see. Are you raising your hand? Victory, you can raise your hand so I can unmute you. Okay. Okay. All right. You can unmute yourself now, Victory.
Can you hear me, ma? Good morning, ma.
I can hear you.
Hello.
Yes, I can
Okay.
hear you.
So I wanted to ask, you said boiling point is achieved when the vapor pressure equals the external atmospheric pressure or something, right? And I was meant to understand that if you go to places like the mountain top where the pressure is actually reduced, then the boiling point of water will actually reduce to less than 100. So I want to ask if you should actually take out the whole external pressure and your liquid is made to boil without even heating it. It boils without like you, I don't know how to put it. Like you take out the external pressure and your liquid is meant to boil. I saw it's actually possible. I want to now ask if the temperature will still increase. Like, would there still be an increase in temperature following that
No,
process?
in this case, what we are looking at is the effects of impurity, if you may say, in a solution. So you have a solvent and you are dissolving a solute in that solvent. So it's not just the whole thing about vapor pressure and all that is coming because of the presence of that solute. So that's what we're looking at, and that's what we're trying to calculate. You're looking at the effect of that solute being dissolved in the solution, the effect on the boiling point of the solution. So the pure liquid has a boiling point on it. So, but when you add solute to this solvent, what effect would it have on it, and how much is this effect? So that's what we're trying to calculate here.
Okay, I understand now.
All right, thank you.
Thank you, ma'am.
Okay, what's the time now? All right, so we just solved this. Now, freezing point, the pressure, so just like the boiling, oh God. So just like the boiling point is very similar to, the freezing point is very similar to the boiling point. So in this case, what you have is the depression of the freezing point. And the reason for this is also very similar in changes in vapor pressure equilibrium. There are more atoms of pure solvent going from solid to liquid than from liquid to solid. So for non-ideal solution, now remember that we said Raoult's law, Henry's law, and all these laws that we've been talking about is applicable to ideal solutions. For non-ideal solutions, they will not obey Raoult's law. The solute-solvent interactions are significantly different from solute and solvent-solvent interactions, and the solution is likely to be a non-ideal solution. But all this have to do with the intermolecular forces of attraction. And if you now have a non-ideal solution, what you're going to get is a deviation from Raoult's law. So you can either have a negative deviation or a positive deviation from Raoult's law. The negative the negative deviation the negative deviation is represented this way. So you can see this is your Raoult's law. This is the plot from your Raoult's law. So if you have a plot that's lower than this, what you say is a negative deviation from Raoult's law. And when you have something like this, so you are having a positive azeotrope, what you have is a positive deviation from Raoult's law. So the maxima and minima in the curves correspond to the azeotrope. So it can either be positive or negative. If the vapor pressure of a mixture is lower than expected from Raoult's law, there is said to be a negative deviation. So this plot has really explained this deviation from Raoult's law. So in systems, in real life systems, you can actually have such cases. Now, for example, the system of chloroform and acetone. When you mix chloroform and acetone together, they are not ideal mixture. Remember that when we started this Henry's law and Raoult law, we said there's really nothing called ideal solutions, but we have something that is fairly good enough that we can actually just manage, just say, okay, for the purpose of this class, this is very similar, so we can say it's an ideal mixture. But in this case, chloroform and acetone, they are not ideal mixture. So they have negative deviation from Raoult's law. And this indicates that an attractive interaction between the two components has been described as an hydrogen bond. So in your acetone, you have the presence of hydrogen bond, which is a stronger bond. So you can't expect the intermolecular force of attraction between acetone and chloroform to be the same. The same thing with your HCl and water. Hydrochloric acid water has a large enough negative deviation to form a minimum in the vapor pressure curve known as a negative azeotrope. That's the curve that goes beneath the Raoult's law. And this corresponds to a mixture that evaporates without change of composition. Now, if the deviation is large, that's if the deviation from Raoult's law is large, then the vapor pressure curve shows a maximum at a particular, oh, we've talked about this. So all this is just an explanation of the previous slides that was shown. Now, this is the example for your acetone and water. So both components have a lower escaping tendency in the solution than in the pure liquids. So when you have your water and acetone in a mixture, the tendency of them forming vapor is lower, and that means the boiling point has been elevated. That's just what it means. If the tendency of if the tendency of escaping, that's the tendency of them forming vapor in the solution, is lower than in the pure mixture. So I think this is another example. If the two liquids end up, I need to move this. I don't know if this is disturbing, but it's covering my screen, and that's why I like to just take it off completely. Uh, so what did I do now? All right, okay, so I think we're on the last slide. So if the vapor pressure of mixture is lower than expected from Raoult's law, there is said to be a negative deviation. So this your acetone, so this is your acetone, and this is your water. So we said something about hydrogen bonding. This hydrogen bonding is a strong bond. It's a strong bond. So what you have is a negative deviation from it makes this more stable. So the hydrogen bond, remember that something with bond strength and stability. This solution, this mixture here, is much stronger than this water or this acetone. So it causes a negative deviation from Raoult's law. If the vapor pressure of a mixture is higher than expected from Raoult's law, there's said to be a positive deviation. And an example of such mixture is your ethanol and your, what do we, hexane? 1, 2, 3, 4, 5, 6. Yes, hexane. So you have your ethanol and your hexane. So with that, we have come to this end of this class, but I would implore you to check out those calculations once more. Unfortunately, we were advised to leave out the solution slide so that you can be more active in class. I don't think I'm going to leave my solution out of the slides anymore because I can see some of you are lost. So I'm going to include it on the next slide. That's for subsequent classes. I'm going to include it on the next slide. We'll probably treat it together before I show you the next slide. So for that reason, all the examples that we treated in the class today, I'm going to send you the solution slide so that for those of you who could not follow in class, you'll be able to catch up. From subsequent classes, you will have it readily on your screen. I think that's with today's class. I have a couple of announcements.